In this second chemical reactions video, I'm going to look at how we represent the chemical reactions themselves. I'm going to start the video by looking at word equations, and then I'll take it to the next level by looking at balanced symbol equations, and we'll finish by looking at a very important theory, the conservation of mass. So if you've watched the first video, you'll know that I covered 4 different combinations of atoms. We looked at a couple of examples where we joined a metal with a non-metal and we got the ionic bonding between them. And then we looked at the combination of 2 non-metals to form a molecule, and they have covalent bonds between the atoms. So if you remember, the 4 combinations were lithium and fluorine, sodium and chlorine, hydrogen and fluorine, and carbon and hydrogen. So if you'd like to have a go at writing word equations for those 4 combinations, we'll pause the video and then I'll go through the answer. So there's the first one. Lithium and fluorine combine together to make the compound lithium fluoride. So you can see on the left hand side of the arrow we've got the reactants. So they're the chemicals that combine in the chemical reaction, and after the arrow we have the product or products. Sometimes there's more than one product, but in this example we've only got one. And there's all the rest. So we've got sodium plus chlorine making sodium chloride, hydrogen plus fluorine making hydrogen fluoride, and carbon plus hydrogen making methane. So we'll take this to the next level now. We'll look at balanced symbol equations. So you can see on the board there I've got the first of those 4 word equations that we wrote before. Lithium plus fluorine making the ionic compound lithium fluoride. So what we're going to do now is write the chemical symbols underneath each of those substances. So there it is there, Li plus F2 making LiF. Now there's a problem with this equation, and that is it's not balanced. So what we mean by balanced is we must have the same number of atoms on each side of the arrow in the equation. So if we look at the lithiums, they're okay actually because there's one of each left and right. The problem lies with these fluorines because we've got 2 here in this F2 molecule, but only 1 there in LiF. So what I sometimes see people doing, and you can't do this, you can't change the formula of a compound. The formula of lithium fluoride is fixed at LiF, so you're not allowed to change it. So how do you do it? Well, we're going to use numbers and we're going to put them in front of the substance. So you can see straight away we need 2 F's because there's 2 there and only 1 there. So the only way we can solve that really is by putting a big 2 in front of the LiF. So in a sense that solved the problem with the fluorines, but it's created another problem because this 2 is doubling everything. So there's 2 Li's now and 2 F's. So how do we solve that? We just put a 2 in front of the lithium, and now that's balanced. We'll just go back to the unbalanced version of the equation, and I'll just show you another way you can think about it just till you get your head around this. So you can see I've shown each particle as an individual atom. So we've got 1 lithium, 2 fluorines in F2, and 1 lithium and 1 fluorine in LiF. So you can see straight away there's the problem, 2 F's, only 1. Remember, you're not allowed to change the formula of anything, so we can't do that. So what we need to do is we need to bring another one of these in. So if I draw another LiF, we've solved the problem with the F's, created a problem with the Li's, so we need another one of those. So when I put those big numbers in front, what I'm saying is I need 2 lithiums, one lot of F2 and 2 lots of LiF. So they're balanced again. So there's the other 3-word equations we looked at before. So why don't you have a go at writing the balanced symbol equations for those 3, and then I'll go through the answer. So there they are there. So we just need to check whether they're balanced or not. And if they're not balanced, we need to put some big numbers in front of substances in the equation. So we'll start with the sodium and chlorine one. 1Na, 1Na, that's fine. 2 Cls, 1 Cl, no. So we need a 2 there to sort out the chlorines, and we need to put a 2 there. So that's actually the same as the lithium and fluorine one. Hydrogen and fluorine, so H2 plus F2 making HF. So we've got 2 hydrogens, only 1, 2 fluorines, only 1. So a 2 there will solve everything. And lastly, the carbon plus hydrogen one, C plus H2 making CH4. 1 carbon, 1 carbon, 2 hydrogens, 4 hydrogens. So a 2 in front of that will give us the 4 hydrogens we need on the left. So we'll just finish this little section with some slightly trickier ones to try. All I've done is look through the GCSE chemistry syllabus and picked 4 of the reactions that you need to know. So again, if you want to have a go, and then I'll go through the answers. So the first one, lithium plus water making lithium hydroxide and hydrogen. 1 lithium, 1 lithium, 2 hydrogens, 1, 2, 3. Right, we've got a problem here. We need more hydrogen on this side, so we'll have a go at putting a 2 there. So does that solve the problem? Well, it gives us 4 hydrogens now. We only got 3 here. So if we put a 2 there, that'll make 4 hydrogens, because remember this 2 doubles everything. So we've got 1, 2, 3, 4 hydrogens. So they're sorted now. Oxygens, we've got 2 oxygens because the 2 doubles the O there, and that 2 there sorts that out. So the oxygens are okay. The only problem now is the lithium. So if we put a 2 there, that's sorted. The next one is the thermal decomposition of calcium carbonate to make calcium oxide and carbon dioxide. So 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens, 1, 2, 3. So that's actually already balanced. The next one is the reaction that takes place in the Haber process to make ammonia. So nitrogen and hydrogen combine to make ammonia. So you can see we need a 2 there to sort out the nitrogens. So how many hydrogens does that give us? 2 times 3 is 6. So we need a 3 in front of here, because the 3 times the 2 will give us the 6 hydrogens we need. And then the last one is the combustion of ethanol. So that's an alcohol. So when it burns in oxygen, it produces carbon dioxide and water. So how will we do this one? We've got 2 carbons in ethanol, so we'll go for 2 in front of the CO2. We've got 5, 6 hydrogens, so 2 in the water. So if we put a 3 there, 3 2s are 6. So all we need to do now is go back and do the oxygens. So we've got 2 times 2 is 4, plus 3, so we've got 7 O's. Just be careful, there's an O in the alcohol, so that means we need 6 oxygens from the O2. So we'll put a 3 there, 3 2s are 6, plus that one there is 7. So they're all balanced now. So in the last section of the video, we're going to look at conservation of mass. A very, very important law in science, which basically says that when chemicals combine, you don't lose or make any atoms. So that's why chemical equations have to be balanced, so that the number of atoms are always the same left and right. So if we think about this balanced equation here for the reaction between carbon and hydrogen to make methane, Let's just suppose we took 1.2 grams of carbon and reacted that with 0.6 grams of hydrogen. How much methane would we make? Well, if you can't lose or make atoms in chemical reactions, then surely the mass at the start has to equal the mass at the end. So therefore the answer's got to be the sum of these two, 1.8 grams. So we'll finish the whole video with this one here. This is the reaction involved in the blast furnace, where you take iron oxide and you react it with carbon to extract the iron, the Fe, and it makes carbon dioxide as a result. So if you want to balance the equation, and then I'll set a little maths question at the very end just to tie in the conservation of mass. The best way to tackle this one is to look at the oxygens first. So we've got 3 O's here and only 2 there. So the best thing is to take them up to 6 on each side. So we'll get a 2 there and we'll put a 3 there. Quite easy now because we've just got single substances, these atoms now. And so if we've got 2 Fe2O3s, that's 4 Fe's. So I'll put a 4 there. And if we look at the carbons on this side, we've got 3 CO2s. So I need a 3 there. We'll just do a little conservation of mass question. So let's suppose you took 24 grams of iron oxide and you made in total 76 grams of product. So that's the iron and the carbon dioxide combined. How much carbon must have been used? So obviously the answer is the difference between these numbers. So to get 76 from 24, we must have used 52 grams of carbon.